Okay, this is video 26.3. We'll be looking at how much energy is stored on a capacitor. Now we said at the beginning of chapter 26 that capacitors are used, among other things, for energy storage. The question is, how much energy is stored on a capacitor? So let's say that we have a partially charged capacitor. There's charge plus Q on this plate, charge minus Q on the other one. The result is that there is a voltage difference V between the plates. And so let's say that we want to increase its charge further by a small amount, dq. So this tells you you're going to do an integral at some point. So if we move dq from the negative plate to the positive plate, we're obviously going to have to do work because there's an electric field set up that opposes that movement of charge. The amount of work we have to do, I'll call it dW, is equal to the voltage difference times the charge dq. But remember, for a capacitor, that voltage difference is the charge on the capacitor divided by the capacitance. And so to find the total work done, required to bring the capacitor up from 0 to its charge Q, we'll integrate from 0 to Q. So we have Q dQ over C, and that works out to be Q squared over 2C. That's a formula you should memorize, but you should also know how to derive it. Oh, and we did that. We integrated to find the total work required to charge the capacitor. The energy stored on a capacitor is the square of the charge divided by twice the capacitance. But this can also be written as 1/2 CV squared, and I'll let you derive that on your own. So if you know the voltage, this is what you use. If you know the charge, this is what you use. And so let's take a hypothetical. Let's say we've got a charged capacitor, and you're going to move the plates apart. The question is, what happens to the energy stored in the capacitor? But it's important to specify that it's disconnected from the battery, because when it's disconnected from the battery, that means the charge on the plates is constant. It does not change as you move the plates apart. V, however, will change. So the formula we're going to use for energy is 1/2, or is Q squared over 2C. Because charge is constant, that's not changing. Now if we move the plates apart, the capacitance for a parallel plate capacitor is epsilon 0 A over D. So we're increasing D, which means that we are decreasing the capacitance. And since we're decreasing the capacitance, that's going to increase the energy stored in the capacitor. And that's very interesting. What do you think, where do you think that energy came from? I'm not going to tell you now. We'll discuss that in class tomorrow. But think about where that energy came from. You're separating the plates in the capacitor. Somehow, the energy stored in the capacitor increases. Did we just violate conservation of energy? Hint, the answer is no. But see if you can figure out why it doesn't violate that. Now let's look at the same situation, except that we're going to keep the capacitor connected to a battery. What this means is that the voltage is constant, because that's what batteries do, is they maintain constant voltage between their terminals. But because charge can move through the battery, that means Q is not constant. And so this time, we're going to use the formula U equals 1/2 CV squared because V is constant. Now we've already established that increasing the distance between the plates decreases the capacitance, and that means the energy stored in the capacitor decreases in this case. So if you don't connect it to a battery, it's very different than if you make a change to the capacitor when it is connected to a battery. Make sure you understand why the battery connections matter, and that you use the appropriate formula, the one that has the quantity that stays the same in it. Now a similar example, you've got a capacitor until that it's charged, the stored energy is 4 joules. So before you have capacitor C with 4 joules of energy stored on it. Then we're going to connect a second uncharged capacitor to it in parallel. And we'll say that those are identical. Now the charge is going to distribute itself equally. So this has charge Q on it initially. When you connect that second capacitor, it spreads itself out, so you have Q over 2 on this capacitor, Q over 2 on this capacitor. Now one thing we can say here is that the initial energy equals Q squared over 2C. Afterwards, the energy on one of the capacitors is Q over 2 quantity squared over 2C. And the energy on the other capacitor is also Q over 2 squared over 2C. And so the total energy is now Q squared over 4C when you add those two together, which we'll notice is half of the original energy, and it is therefore 2 joules stored in the combination. Question is, what happened to the other 2 joules? Somehow, when you connected the second capacitor, 1 joule is now stored on each capacitor. What happened to the other 2? Did it just magically disappear? That's another mystery question that we're going to talk about in class tomorrow. So tomorrow I'm going to check problem 23, which is not terribly difficult, but more importantly, we're also going to talk about where that energy went. So come prepared to discuss that.